Today's lecture. The first element which we are going to look today would be a uniform flow. The first element. It's the most basic element. What is uniform flow? We know already about a uniform flow. Uniform flow and non-uniform flow, this is something which we already read before. Uniform flow is a kind of flow in which at a particular time there is no variation with respect to space. That's what we know about a uniform flow. So consider a uniform flow with velocity v infinity oriented in positive x direction. Okay, so these straight red lines which you are looking at, these are the streamlines, and we already said that each streamline is can be defined by a stream function psi. Psi equals to a constant, means a streamline. Just for an example, let's say this is psi equal to 1, this is psi equal to 2, psi equal to 3, and so on. Now this could be any constant. It's just an arbitrarily, I have taken 1, 2, 3 as the constant. So the red lines, parallel lines which you are looking at, this is a streamline, and we already know about a streamline, that a streamline is something which is tangent to the velocity vector. So that is the reason that you are looking at straight parallel streamline, and this is the kind of uniform flow which we are considering, where the flow is going towards positive direction. You can look at the arrows here, and it's of a single magnitude v infinity. Okay, so such kind of flow is a uniform flow. It is the most basic flow element which we have considered. Now this dashed line which you have seen here, which you can look at here, the black line, this represents potential flow, phi equal to a constant. Psi equal to constant represents a streamline, and phi equal to constant, it's a perpendicular line which we have drawn. And a little bit afterwards we would see that why the stream function and potential function are orthogonal. We say two functions are orthogonal. I hope that you have already read about it in your mathematics, that when two functions are orthogonal, perpendicular to each other, for example sine and cos, these are orthogonal functions. So psi and phi, stream function and potential function, they are also orthogonal function. So a little bit afterwards maybe you would look into it. What do I mean by that? Okay, so a uniform flow is a physically possible, incompressible, irrotational flow. So we are saying that this is a uniform flow which would be an ideal flow, and an ideal flow is incompressible, irrotational flow. Incompressible meaning by del dot V would be 0, and irrotational flow would mean that del cross V would be 0. Now, for such kind of flow, we can define a velocity potential for a uniform flow such that del phi equals to V. If that's the case, then first thing which I can say is del phi by del x would be my velocity u, and the u component of velocity is given to me here as V infinity. Second, I can say that del phi by del y would be equal to the V component of velocity, and for my case of uniform flow, you would see that V component of velocity is 0. Okay. Now, just to be very clear, I have taken my uniform flow here in such a way that the velocity is directed towards x direction. That much easily. You can take a uniform flow in such a way that it would be going towards positive y direction, or towards negative y direction, or towards negative x direction, or even you can take a uniform flow at an angle theta from the x-axis. The only thing would be, for a uniform flow, that you should see parallel streamlines. Okay, that's what you need to be sure about. Otherwise, it's not always the case that uniform flow can only be in positive x direction. It could be in any direction, it could be in any orientation. For a flow to be uniform, it's a simple thing that it should not change with respect to location. That's what a uniform flow is. Okay, let's move a little bit ahead. If I integrate this equation number 1, with respect to x, we will have phi. It's a partial differential equation, so it would be v infinity time x plus fy, where f of y, this function fy is a function of y only. Fy is a function of y only. Okay. Similarly, if I integrate equation 2, integrating equation 2 with respect to y, I would get phi equals to a constant plus g of x. Okay. Now g is again another function, and gx is a function of x only. If I compare 3 and 4, comparing these two, I can say that phi, this function of x only, looks like to me it's this, and it looks like to me that it will be something like this, meaning by my phi would be v infinity x plus a constant. So that would be the value of phi. Okay, that would be the value of phi. Now, since we are generally interested in velocity, and velocity is given by del of phi. Velocity is given by del of phi, and we also know that derivative of a constant is 0. Therefore, we can say that our phi is simply v infinity times x. We can say that our phi is nothing but v infinity times x. It is as simple as that. So in this way, we got our phi for uniform flow, for this particular uniform flow, where the velocity is directed towards positive x-axis. My potential function came out to be v infinity times x. For the same flow, if I want, I can find my psi stream function also, and I know about it that del psi by del y is my u component of velocity. For this case it is given to me as v infinity. My del psi by del x would be minus times v, and there is no y component of velocity, it is 0 for this particular case. If I do the same thing which I did before, that I integrate equation 7 with respect to y, integrating equation 8 with respect to x, if I would do that, I would find finally that my psi would come out to be v infinity times y. How did I get that? Integrating equation 7 with respect to y and equation 8 with respect to x, and then comparing them. If I did that, then my stream function psi would come out to be v infinity times y. Now look at equation 6 and equation 9. My potential function is v infinity times x. My stream function is v infinity times y. These two functions in itself, they are orthogonal. And how to find if two functions are orthogonal or not? I would like you to look at your mathematics and find out there is a way in which you can find if your functions are orthogonal or not. But just by looking at it, equation 6 and 9, you can say that your phi is perpendicular to your psi. Okay. Now, we found our phi, we found our psi. Now for this kind of flow, which is a ideal flow, the next thing which I would like to find would be circulation. Just to tell you, just to remind you something, this complete potential flow theory, it started developing so that people could study lift over an aerofoil. So mostly this way of analyzing problem came from the application of aerodynamics, and aerodynamics generally deals with where you have an object flowing in air. Okay, that's where and that is known as the study of aerodynamics, flow in air of an object. So this complete study came from there. This way of studying mostly was developed for aerodynamics, and in aerodynamics we are mostly interested in that if an object is flowing in air, then how much lift would be developed. Lift is the force which is acting perpendicular to the direction of flow, and how much drag is acting. Drag is the force, just like a friction force, which tries to stop the motion of and drag is the force which acts in the direction opposite to the motion of the body of the solid. So for finding lift and drag, one way to do that, this you would see afterwards, is to find circulation. And circulation, we already found out that you can find circulation if you take a closed curve. For example, in our case here, we have taken a closed curve, this black dashed line, if you would see, this rectangular line of length L and height h. It's a closed rectangular curve C, and simply find circulation. And circulation is nothing but v dot ds. For example, for this much portion of ds, the velocity would be v infinity. For this vertical portion of ds, the velocity would be 0. For the above portion of for the above ds or a portion of this curve C, velocity would be again velocity is in this direction v infinity, and we are going towards opposite direction. So if you would look at your previous fluid kinematics part where I covered circulation, you would see how circulation is found. In this case of ours, if we are trying to find circulation, this circulation we know about is closed integral over a curved surface v dot ds. Now circulation for this particular case of uniform flow, v for our case is a constant v infinity. You can bring it out, and ds closed, if you take an integral over a closed curve, this quantity would come out to be 0. Any curve which is closed, okay, and you take ds, it would come out to be 0. So it means this is v infinity times 0, which is 0. This is one way of finding it. Why? Because of this, that line integral of ds around a closed curve is identically 0. But if you would remember, I gave a relation between circulation and vorticity, and we said that circulation can also be found in this way. Now I am taking S means area integral, surface integral. I should rather write A, actually that would be a good way, dA. Okay, circulation can also be written in this way, and we already know that we have taken irrotational flow, and for an irrotational flow, del cross V is 0. If I would put this back in here, then I would get my circulation to be 0. Meaning by that circulation for this kind of case, for a uniform flow is 0. And why I am finding circulation? Because you would see a little bit afterwards that circulation is directly proportional to lift. That's why we are finding circulation here. So anyways, that was my first elementary flow, basic flow element, and that was uniform flow. Now for all the flow elements which we would see afterwards, this is going to be the way that either the velocity profile would be given to us, from that we would find psi and phi and then circulation, or the stream function or the potential function is given to us, and from there we would try to find the velocity and then find circulation. Okay, but it would be the same way throughout. The way the procedure is not going to change, and you would see that in our second case also. So the second case which we are going to study would be source flow. The first case which we studied was that of a uniform flow, and you were seeing parallel lines. The second case which we are going to study is known as a source flow or a sink flow, and this is the kind of flow which does not exist in reality, but we can use it and we can add with certain other elementary flows, and we can study real kind of flows. And this is something which you would see a little bit afterwards, maybe in our next class. Now, what is a source flow or a sink flow? Source flow is that kind of flow in which you would see the flow is coming out radially from a single point. In a two dimension, you would see that flow is coming out from a single point, just like that here. Source flow, you would see an origin point O, and then you would see radial lines coming out. These black radial lines are my stream lines, which are tangent to my velocity vector, and each radial line represents a streamline psi equals to a constant. Okay, I have taken a point, let's say a point P, which is located at a distance r radially and at an angle theta from, let's say, x-axis. As you move along a radial direction along r, the velocity is going to change. So let's say if r equals to r1, then velocity would be vr1. If I change r to r2, the velocity would change vr2. But for a fixed value of r, let's say for a fixed value of r, let's say r1, if I go around theta, then velocity is not going to change. I hope you understand this, that the velocity will only change if I am going along r. For a fixed r, if I move along theta, velocity is not going to change. So my streamline are radial lines, and my potential flow lines would be circular lines. And like I said before, that my stream function and my potential function are actually orthogonal to each other, and a little bit down the analysis you would see also that my stream function and potential function would come out to be such that they are orthogonal to each other. So source flow is when velocity lines are moving outwards from the center, and sink flow is when the velocity vectors are converging towards a center O, which you can see here. Okay, that the velocity lines and my stream lines are moving towards a center. So source flow and sink flow, it's one and the same. I can use negative sign for one and positive for another, and source and sink flow would be the same thing. Now consider a two-dimensional incompressible flow. It's a two-dimensional incompressible flow. Whenever you would hear incompressible flow, this thing should come to your mind, that del dot V is 0. Incompressible flow means del dot V is 0. So for a 2D incompressible flow where all streamlines are straight lines emanating from a center point O, the velocity along each streamline vary inversely with the distance. As I am moving away, my velocity is inversely proportional to my distance r, meaning by Vr is inversely proportional to r. Okay, and this is something which I will prove mathematically also. Okay, it is not something which I am imposing on you, but I will show it to you mathematically also. That velocity varies with distance from O. Now let the radial velocity be Vr and tangential velocity be V theta. In our case, there is no V theta. In the case which we have shown here, for a source flow or for a sink flow, the only velocity are the radial velocities. There is no tangential component of velocity. There is no V theta. Whatever there is, it's all Vr. If that's the case, then I know that for incompressibility del dot V is 0. So I use, if I want to find my stream function, I would use incompressibility del dot V0. If I want to find my potential function, I would use irrotationality del cross V0. Okay, I can use both. So for incompressibility, I know that del dot V is 0. Now in this case, I cannot take xy axis. I mean, I can take xy coordinate system, but that would make my problem difficult. So instead of taking x and y coordinate system, I would take r and theta coordinate system. And if I would take r theta coordinate system, then my del gradient vector would be modified, and I would be writing it in this way: 1 by r del by del r times vr. Actually, let me write this as this r plus 1 by r del by del theta of v theta is 0. Since v theta is 0, so this complete thing is 0, and my equation would come out to be del by del r times vr equals to 0. And if I integrate, I would get VR is equal to C divided by R. I got this after integrating. So even mathematically, see, I got this thing that my radial velocity is inversely proportional. VR is inversely proportional to my radial distance. Now here, this C actually gives me how much flow rate is coming out of my source or sink. Okay, how much flow rate is coming out of source, or how much it's going inside the sink. So C actually gives me an idea about the strength of my source or sink flow. If C is positive, then I have a source flow. That means that VR would be radially outwards. If C is negative, then I would have a sink flow, meaning by that VR is inwards. Now, what is C? Can we find out, C in terms of those parameters which makes more sense to us? Yes, we can do that. And this is something which I would do in next class. I would like you to go and read that. Just to give you an idea that whatever I have covered, whatever I'm covering since my last